Okay. Good morning, everyone. And we had started with continuous time Fourier series. We had solved one simple problem on that. And in continuation to that problem, so we'll be analyzing it. So how it is like having certain k values. Okay. So I had given some k values and exponential Fourier series representation of it. I had been given. Okay, so this is what the definition is all about. Okay, so we have x of t. Okay, so we have x of t that would be equal to sigma k equals minus infinity to plus infinity. Okay, so can anyone tell me what is x of k? What is x of k? So it's a complex Fourier coefficients. Okay, so x of k is complex Fourier coefficients there, right? So now you have the exponential way in which it is given, that is e power j into k into omega naught into t, right? So now you have got the value of omega naught. Okay, so you have got the value of omega naught as, what's the value of omega naught? What's the value of omega naught? So that would be equal to pi by 2. Okay, so I've already like added this image file also here. Okay, so where you will be having x of k being written first, and next you will be having the value that is written for omega naught as pi by 2. Okay, so after having certain values of k, okay, so what you did was for x of 0, that's the value that is being given as the DC value or the average value as 1 by 2. Okay, so you have got the value of x of 0 to be equal to 1 by 2. Okay, similar minus 2, next plus or minus 3, next plus or minus 4, next plus or minus 5. Okay, so these are certain values that you might give. You may go up to plus or minus 6, plus or minus 7. Okay, so you observe the pattern how it is. Okay, so one you will be getting plus and the other one you will be getting minus. Okay, and the other value it might be some 0 or something like that. Okay, so see to it that you are going to observe the values that has been written over there, right? So now after substituting the values of k and x of k there, so you will be getting x of t. Okay, certain values whatever it has been listed here in this image file. Okay, so you will be having 1 by 5 pi into e power minus j into 5 pi by 2 into t. Okay, so this value here, okay, so it will be 0 there, right? So what okay, so whatever the value that is x of t that has been written, so you will be having a positive value, okay, and the negative value, and you will be having 0 here. So what it means is, so this one over here, that you will be having the value of k to be equal to 2. Okay, so this 0 here, which will be k equals to 4. If you have done the problem, you would definitely come to know that for k is equal to 2 and k is equal to 4, you will be getting 0. Similarly, you will be getting for k is equal to minus 4 and k is equal to minus 2 also to be equal to 0 there. So only what you are going to get there is the odd numbers. Okay, so odd numbers whatever that you give. Okay, so whatever that you give for x of k value, okay, k value would be plus or minus 1, k value would be plus or minus 3, k value would be plus or minus 5. So okay, so whatever the k values that has been listed out here, so for those k values you are going to get the terms here. Okay, so if you observe it carefully, so later on you will be getting the value of x of t with the 1 by pi term which is being taken as the common factor. Okay, so unless and until you do the problem, if you substitute it, and you will be getting it. Okay, so unless and until you will not be able to understand. Okay, I want every one of them to do the problem. Okay, so whatever the values that you put there, analyze it. How we are going to analyze it? Okay, so you have two set of numbers, that is odd numbers and the even numbers there. So you are going to get the values. Okay, the non-zero value that you are going to get, that would, okay, so you are going to have a waveform which will be having only the odd components that are being present, and the even components are set to be equal to 0 there. Okay, so let me move on to the next one. So how did I analyze it? The exponential Fourier series, I just like explained it properly. So you know that what the DC value is all about. Okay. So what I'm going to talk about here is, so it is the non-zero harmonics there. Okay. So non-zero harmonics that you are going to get in any waveform. Okay. So subject to frequent oscillations and all. So that would be generally termed as an harmonics with the double the value of frequency, triple the value of frequency, 5 times the value of frequency. Okay. So odd terms which are being associated. Okay. So that is 1 time the frequency, that is nothing but the normal frequency there. Fine. So now you will be having 3 times the frequency, 5 times the frequency. Okay. So just what I wanted to write here. So omega naught, 3 into omega. Is what it has been listed out here: 3 into omega naught, 5 into omega naught, 7 into omega naught. Okay, so these are nothing but this is the fundamental frequency, that is omega naught, 7 times the fundamental frequency, whatever that has been listed out. It is subjected to oscillations like this. Okay, so I'm just giving you an overview how would be the oscillations, and this would be the oscillations of the harmonic contents that are being present there in any wave there. Okay, so I have a given wave. Okay, so harmonic contents that are being present there in the wave are subjected to the like n times the number of like the frequency that is associated there. Okay, so now when I'm talking about the non-zero harmonics here, okay, so one thing what I wanted to highlight is, so harmonics h of k. Okay, so whatever that is there. So here in this given Fourier series representation, h of k value, that would be, it is subjected to odd harmonics only. So whatever the non-zero value that you are going to get, it is subjected to the odd harmonics in the given problem there. Okay, so odd harmonics that are being present, and the h of k, that is representing the harmonic content, so that needs to be analyzed here. So I want what is h of 1, next what I want here is h of 3, and similarly I want h of 5 there. Okay, so that is what it has been listed out here. Okay, so h of 1, h of 3 and h of 5 needs to be computed, right? So h of 1, h of 3 and h of 5. So let me go ahead quickly. All right, so that is, you will be having two functions here. Okay, observe carefully what I'm going to write: x of 1 e power j. Okay, the k value would be equal to 1 there. Okay, so the k value, e power k, this k value would be equal to 1 omega naught into t. All right, plus x of minus 1, that is e power j k into omega naught into t. Yeah, sorry, this is a negative sign here. Okay, so x of 1 e power j into k omega naught into t, x of minus 1, this is the value of k here. Okay, so this is the value of k, e power minus j k into omega naught into t there. Okay, so if you observe carefully, the value of k would be equal to 1. All right, so the value of k would be equal to 1, the harmonics content here. Okay, so I'm analyzing with respect to the harmonics content. So x of 1 and minus 1, if you analyze it properly, it is nothing but the symmetric nature there, right? So if you have the symmetric nature of the wave, so minus 1 and plus 1 value, which is already being present there, this is with respect to the k value. Okay, so this is with respect to the k value for a non-zero harmonics. So x of 1 and x of minus 1, what you are going to get? So that is from the complex Fourier coefficients. Okay, so that is from the complex Fourier coefficients. Okay, observe it carefully. Okay, so x of 1. Okay, what is x of 1? That would be 1 divided by pi. Okay, e power j, what is omega naught? Pi by 2 into t, plus x of minus 1, that is also 1 by pi e power minus j into pi by 2 into t. Okay, so that is what you are going to get there, and further simplifying it, so what you will be getting, what you'll get? Okay, so that would be 1 by pi is taken as a common factor, e power j into pi by 2 into t, plus e power minus j into pi by 2 into t. Okay, so what is the value there? E power I theta plus e power minus I theta. Okay, what is its value? 2
I sin theta.
Cos theta.
cos, man. It is cos. Okay, so 2 cos into pi by 2 into t. Okay, so dividing it by pi. Okay, so this is what you are going to get it here. So 1 divided by pi is taken as the common factor. This is where the complex notation of any sinusoidal or the cosine function is being dependent upon. Okay, so see to it that you get an understanding of that. Okay, so h of 3, similarly, I'll leave h of 3 and h of 5 to you, the non-zero harmonics that you are going to get. So compute this h of 3 and h of 5, and you can understand how did I compute h of 3 and h of 5 there. Okay, so x of 3 plus x of minus 3. Okay, let me write the Fourier coefficients first. Next, e power j into 3, that is into 3 into pi by 2, omega naught into t there, that is e power minus j, okay, 3 into pi by 2 into t. Okay, so this is x of 3 and x of minus 3 are the complex Fourier coefficients that are there, right? So x of 3 value that you are going to take here, so you are going to substitute it, okay, and you are going to get the answer. So I think x of 3 is minus 1 by 3 pi here. Okay, so x of 3 and x of minus 3 have the same values. X of 3 and x of minus 3, that will be equal to minus 1 divided by 3 pi. Okay, so that is where you are going to get the values here. Okay, so that's how you can compute the non-zero values. Okay, listen to this carefully. So you are going to compute the non-zero harmonics if it is asked. Okay, observe the question properly what has been asked. Okay, so you need to write the exponential Fourier series representation. You can stop up to x of t. Okay, so if you can stop till x of t, okay, so this non-zero harmonics, if they ask, okay, so the non-zero harmonics, if they ask, then only you need to write it. All right, so non-zero harmonics, I told you how it is being subjected, or any wave that is to be considered, it will be having either the odd harmonics and even harmonics will be equal to 0 there. Okay, if it is having odd harmonics, the even harmonics will be equal to 0. If it is having even harmonics, okay, so the odd harmonics will be equal to 0 there. So that is where the Fourier constants or the Fourier coefficients is being dependent upon. Okay, so see to it that you are not going to forget such things. Okay, so repeat it as much as possible. Okay, so let me go on to the next theorem. Okay, let me go on to the next theorem. Okay, that is theorem 3.2. So what was theorem 3.1? Okay, can anyone tell me what was theorem 3.1? So it was subjected to the orthogonality nature, right? Orthogonality nature. Okay, so where you will be having the value that will be equal to that is the complex notation and it's the conjugate of it. Okay, so once you have both of the things, okay, so once you take the integral part, okay, so you are going to get it as 0 or 1. So 1, if you have the value of both the constants which are there, which is equal, you are going to get the value as 1 then. Okay, so in other cases it will be equal to 0. Okay, so it is subjected to the symmetrical interval over the period. Okay, so that is where you are going to get the orthogonality of the complex exponentials there. Okay, so one more thing, what is there in theorem number 2? X of t, okay, is subjected to the Fourier series expansion and you will be getting x of k. So from x of k you can find out x of t. Okay, so given the complex Fourier coefficients, you are going to find out what is the analytical way. After expressing x of t in analytical way, you are going to get it as x of t as the exponential Fourier series representation. So now this theorem, what I'm going to state here is, so you will be having x of t which will be using Fourier series there. So next, once you take the conjugate of x of k, okay, so that will be equal to x of minus k. Okay, so for all the values of k, okay, so if and only if x of t is a real function, x of t is a real function of t. So of t is a real function of t. So what you are going to get? You are going to have the complex nature of x star of k, which is nothing but the complex value there. So that would be equal to x of minus k for all the values of k, if and only if x of t is a real function of t. Okay, so if x of t is a real function of t, So then x star of k, that would be equal to x of minus k then. Okay, so see to it that you are going to carefully look into this theorem. Okay, so let me start with the proof here. Okay, so now what is being listed out? So x star of k, that would be equal to x of minus k here. Okay, so x star of k, that would be equal to x of minus k. So if x of t is real, for all values of k, then. Okay, so I know that x of t is real for all the values of k. Then I can say that x star of k, that is the conjugate of the complex Fourier coefficients, that would be equal to x of minus k then. Okay, so once you give the value of k here, so this conjugate and minus value of it, that would be equal then. Fine. So now let x of t be real. Then x star of k, that would be equal to 1 divided by t integral under the limit. Okay, so that is over the time period, x of t e power minus j into k into omega naught into t dt. All right, so this is also in terms of the conjugate there, right? So now what happens here, if the conjugate is taken into picture, only the signal that is there in terms of the conjugate, that is x star of t, that needs to be analyzed here. So minus becomes plus. Okay, so understand the nature quite clearly. That is x of k, you have x of k equation that is there. So once you take the conjugate of it, so you will be having 1 by t integral over the time period x of t e power minus j into k into omega naught into t dt. So once it is subjected to the conjugate nature, whatever the values that is listed out here, so it is x star of t, right? Next, the minus value. So once you have the negative values, it will be turned into positive, right? So that is how it has been representing in terms of the complex nature, right? So e power j into k into omega naught into t dt. Okay, so now what is being asked here? So how we are going to write it? So x of t is real. So if x of t is real, what you are going to write? Can anyone tell me if x of t is real? So how I can write x star of t? Yes, complex nature. So I'll be having a complex number, right? So now I need the real part of it. Okay, so what do I need to do? So if x of t is real, that is what it has been asked here. So I'm taking the conjugate of it, that is x star of k, that would be equal to x of minus k. If x of t is real for all values of k, x star of t, that would be equal to, what's the value? Yeah, it is x of t there. Okay, so how did I write x of t? I'm only concerned with the real part here. Okay, so what is the real part? It is x of t. Okay, so once you have a complex number, okay, understand it carefully what I'm going to tell right now. So x of t is said to be real. Okay, so here I have x star of t. Okay, so if I say that x of t is a real one, x star of t, that would be equal to x of t. Hope you're getting what I'm saying here. Okay, so that is where it is being representing for a complex number. So you can understand whatever that is written over there. So real part of x of t. Okay, so it is like vice versa also. So once you have a complex number, the complex conjugate of it, so that would be with respect to the real part itself. So that the imaginary part will be having a change in the sign. If you are subjected to the conjugate part, okay, that real part of it would be the the real part of the complex function then. Okay, so remember one thing, x star of t, that would be equal to x of t for x of t being real. Okay, real values, the real part or real values that are there for all the values of k. Okay, this is with respect to the mathematical aspect what I'm talking here. X star of t, that will be equal to x of t. So for all the real values, okay, so that's how I can write this. Okay, so now I have x star of k, that would be equal to, okay, that would be equal to 1 divided by t integral under the time limit, that is x of t e power j into k into omega naught into t dt. Okay, so what I can write it, I can write it as x of minus k. Okay, so for x of k you would have minus j here. Okay, so for x of minus k, the k value is being changed to minus k there, so that's the reason it gets changed to positive k. So I can write it as x star of k, that would be equal to x of minus k. Okay, so this is how I can write the second theorem, that is theorem number 3.1, which was with respect to orthogonality. 3.2, that is x star of k, that is equal to x of minus k there. Okay, so that's how we can prove the theorem there. Okay, so one more thing, that is the corollary statement, what I wanted to highlight before winding up the class. The corollary, okay, so that is x of k, that would be equal to a of k plus j times b of k. So where a is the real part and b is the imaginary part with respect to the complex Fourier coefficient. So how I can write x star of k? A of k, x star, complex conjugate. Complex conjugate, can anyone tell me? I have the constant a of k and b of k. So I can write it as a of k minus j into b of k. So that's how I can write this one. Okay. So I hope Mohan is there in the meeting.
Be present, sir.
Yeah, so this is what I wanted to highlight here. So x of k is with respect to the real part and the imaginary part. So what did I do here? I did the complex conjugate. What is the change that needs to be done? I just changed the imaginary part with respect to the complex conjugate there. Fine. So how we are going to take the magnitude of the complex number?
So root of a square plus b square.
Exactly, that's nice. Okay, so x of k, okay, now I'm connected with respect to the magnitude here. So I've got x of k and x of minus k there. Okay, so both the terms are said to be equal once you have the magnitude nature of it. Okay, so once you take the magnitude of it, both the values are said to be equal to each other there, right? So once you have two types of spectrum, okay, I'll discuss in detail. So you will be having the amplitude spectrum, which is with respect to the amplitude. So how you are going to get a plot and of a given waveform. The second one is with respect to the phase one. That we will be calling it as the phase spectrum. Okay. So what I want to remember, what I want you people to remember is, so once you are connected with respect to the magnitude of the Fourier coefficients, so once you have x of k and x of minus k, so both the magnitudes must be equal. Okay, so that is one more statement with respect to the corollary here. Okay, so that is generally with respect to the amplitude spectrum, and it is said to be an even symmetry. Okay, so now you will be having the phase spectrum that is there. So that's also symmetric with respect to the vertical axis. This is the y axis there. Okay, so these are the concepts which I wanted to highlight. Okay, so certain concepts are already there. Okay, so I want you to understand them properly, and we can have few more discussions in the coming classes. So I'll be sharing few more videos in the WhatsApp group. Okay, so see to it that you go through the videos and understand it properly. If you have any doubts, do ping it. Okay, so do send a text message or something like that. I'll be able to reply. Okay.